All right.
Thank you.
Hi, good afternoon. See a lot of familiar faces and names. Welcome back for our fourth installment of Journey into Engineering. Tonight, we are going to visit with our electrical engineering department with Dr. Jens Munk, who has a great demonstration with music and engineering with some really big speakers. So, once again, if you're new and you haven't joined us before, my name's Nicole Massey, and I am the advisor that helps our incoming students up to the first 30 credits as you come to UAA with all of our engineering programs. So before I hand this off to Dr. Monk, just go over some real quick Zoom etiquette. Um, Feel free to ask questions throughout the demonstration. There will be a question and answer portion that ends the session, but please keep your mic muted unless you're asking a question, just to keep the background noise to a minimum. If you'd like to keep your camera off, that's fine. However, feel free to turn it on. Just be aware of what is surrounding you because it is broadcasting. So we're going to have our first we're going to have our demonstration, and then Dr. Monk will talk to you a little bit about the electrical engineering program and what you could expect. And then we'll open it up for questions and answers from the audience. So Dr. Monk, I'm going to turn this over to you.
Thank you, Nicole. And can everybody hear me okay? I hope. Okay. So I got into electrical engineering a little bit late in life, despite the fact that my dad was a professor at Ohio State in electrical engineering. And I was really into audio equipment and stereos and sound systems and all that kind of stuff. And I remember, I was always upgrading my amplifiers and things like that. And my dad basically set me straight one day and said, the thing that really matters are the transducers. And I said, well, what in the hell is a transducer? And he said, well, it's the thing that converts one form of energy into another. And so speakers can convert one form of energy into another. Specifically, they're taking an electrical signal that's coming in through the back and converting it into a mechanical sound wave, a pressure wave. And if you are interested in records, I know that a lot of people are kind of getting back into vinyl for good reason. I never got out of it. It's just the most wonderful format in the world. But with a record player, or a turntable, as people in the hi-fi world refer to them, you're literally converting mechanical vibrations from the record groove into a very low electrical signal that you're amplifying it, and eventually it makes its way to your speakers, where that electrical signal is converted back to a mechanical system, or to mechanical waves. So it kind of completes the cycle. So everything in between what we call your phono cartridge, that thing that converts the mechanical energy to electrical energy, and then it's a transducer, and your final transducer is again your speaker, which is again converting your electrical signal to mechanical energy. So these are speakers, and they don't look like speakers, and the reason is most of you are probably not familiar with electrostatic speakers. And I'm just going to rotate these sideways so you can see that they're actually quite thin. And there's actually two parts to the speaker. There's this electrostatic panel, and this is what we built. Well, we built the whole cabinet and all that, but we actually built these panels, and they're going to play the high frequencies and the mid frequencies. So I'm going to kind of demonstrate what I mean by high frequencies and mid frequencies. And then underneath here, you see a woofer, which I'm sure all of you recognize, and you probably know that, woofers play low frequencies or low tones. So in building these panels, I should kind of maybe draw a little picture of how they work and how you might you know, input an electrical signal to these panels and have that converted into a mechanical wave. So what we do is this. I'm going to take a piece of mylar, which is just this incredibly thin, clear. It kind of looks like saran wrap. It's actually thinner than saran wrap. It doesn't stretch the way saran wrap does. But what I would do is stretch it very tight. And we would even do it right here on a table in the lab. And then what we would do is take some of this 3M double stick tape. It has a little bit of thickness, about a 32nd of an inch. And we would lay out strips of tape. You can see the tape strips in here. We then glue this panel to the mylar. We basically stick it, but it's not touching the panel because that double stick tape is keeping it from touching the panel. Then what we do is we have to paint some very slightly conducting material on the mylar so that we can put a huge static charge on it. And then we're going to mate this panel with another panel to create a sandwich. So if I were to turn this speaker around, which I'm going to do right now, you can see that there is, can you see that okay, Andrew? Um, there is perforated metal on both sides. So basically this is a sandwich. There's also double stick tape on this side. So in between this double stick tape is the mylar, and the mylar is the thing that's going to move. Okay, let me just kind of draw on the board what we have to do here. So should we use color? Yeah. So purple is going to be the mylar. So I'm kind of drawing a side view. So this is a side view of the purple. Okay. If you can see that. Oh, that's not a very good. These things never work. The only thing that ever works for me is black. I'll let red be the tape. So, you know, we kind of put tape every so often. Maybe this is kind of a top view of it. And then maybe we'll make the black the perforated metal panel. And the other thing I should notice about this panel, if you notice, it has a lot of holes in it. So when I was looking for panels that this would work for, what I did is I looked for panels that had the most holes per unit area. And if you ever order this stuff, I found a place in Seattle that sells all sorts of perforated metal. There's actually a specification for the percent of open space per unit area, and this was like the biggest I could find. So, okay, here is the metal panels, and I said there's one on either side. So there's going to be one on one side, and there's going to be one on the other side. Okay, so that's kind of what our sandwich looks like. And actually, when you put both those perforated panels together, even though by themselves they're kind of flimsy, they actually stiffen up really nicely. So the next thing we're going to do is we are going to apply a huge, huge static charge to our mylar. So we're going to charge it to around 2000 volts, if that sounds cool. Enough to really maybe give you a shock. 2000 volts. And so one of the things, hey, Andrew, can you show the crossover network? Is it on there? Okay. So if you look at this speaker is a little unusual because normally you don't plug speakers in. This speaker gets plugged in, and the whole reason is we need a way to charge that mylar to a couple thousand volts. So this part of the circuit, this step-up transformer, and this circuit right here, it's called a V-large stepper circuit. The whole purpose of that circuit is to take 120 volts from the wall, 120 volts of alternating current from the wall, and convert it to 2000 volts DC. Okay, so then well, that doesn't make music, but what does make music is we're going to take our signal and we're going to connect our signal, and I'll use maybe red and black because that's generally what they do for left and right channel. So I'll connect one of my panels to one channel of my stereo and the other to the other channel. And this right here is where my music is being input. Okay, so what's going to happen is this. I'm going to draw my panel here again. I'm going to have this huge static charge on it. Okay, I'm really going to expand things so we can see it. And then I have my two panels. I have them really separated now, just to give you an idea. So what happens when the voltage is positive, there's an electric field going in one direction from one panel to the other. And when the voltage is negative, the electric field is in this direction between these two panels. So this is kind of an electromagnetics problem. This is right up my alley. So what happens is when you put charge in an electric field, that charge feels a force. So what happens is the mylar gets pushed this way if it's a positive electric field, and it gets sucked back this way if it's a negative electric field. So as your signal is changing back and forth, it's causing that mylar to vibrate back and forth, and it's going to create sound. That's kind of how these things work. But the other thing that needs to happen, I didn't show you everything about this. Um, we need the voltage across here to be really big as well, a couple thousand volts as well. So we need what's called a huge, well, it's a huge step up transformer. So whatever voltage I put in on one side, it's 100 times bigger on the other side. So 10 volts on this side becomes 1,000 volts on this side. And let me just, if Andrew can go back to my crossover thing, we can show you what I'm talking about in the circuit. So this right here is a it's called a step up transformer. It's a huge step up transformer because it takes 1 volt and makes it 100 volts, or 10 volts and makes it 1,000 volts. Of course, the price you pay is the current is a lot less. So these basically are high voltage but very low current. And of course, down here we have just the regular woofer. So the other thing that a speaker has to have is a way for to take the incoming signal and to kind of divide it into what you're going to send to the electrostatic panel and what you're going to send to the woofer, and it's all going to depend on the frequency. So the really low tones we want to send down here, the high tones we want to send here, the high and the mid tones go here. So what you're going to notice in this little experiment I do is that as I increase the frequency from low to high, initially all the sound is coming out of here, and when I get high enough, all the sound will come out of here. And the circuit back here that does that, well, we have actually two circuits. We have what's called a low pass filter, which passes only low frequencies, and we have a high pass filter, which passes only high frequencies. So the low pass filter goes to this, and the high pass filter goes here. And the circuit that does that is a simple little circuit. It's just the rest of the circuit that I haven't talked about, which is right there. Okay, so basically that's how these things work. I mean, the art of designing speakers is you kind of knowing. Oh yeah, I sure can. So what were we talking about? The filters. Yeah, the filters is right here. And if you take my 353 class, you'll learn all about low pass, high pass, band pass, notch filters, and all of this stuff will make a lot more sense. So there's actually in these kind of simple speakers, there's a lot of what we teach in electrical engineering. There's electromagnetics, there's circuit theory, there's electronics, because what I haven't showed you is this V large stepper circuit involves diodes and other more complicated devices. But anyway, there you have it. And so what I thought I would do was kind of show you a couple things that these speakers do. Um, because the one thing that you might notice is that they're pretty large. And as a matter of fact, if you're used to normal speakers, you might have a woofer and a tweeter. And a tweeter might be something that's has something that an element that vibrates that's about 1 inch or even less than an inch in diameter. These things are huge compared to that, and this is where our high frequencies are coming from, like very high frequencies. And so this is again very large, and when I say large, I mean in terms of wavelengths, and because of that, what's going to happen is you would think that because they're so big that they really project sound uniformly everywhere, but in fact, the exact opposite is true. What we're going to see is as the tone, as the frequency increases, um, you really have to be almost in front of them to hear them. You notice a marked drop off in the level of sound as you move around the speakers. So we call that directionality. These speakers are very directional. So if you listen to them, they have to be pointed at you. So you have to be in the right seat. They don't radiate in a nice big blobby pattern. They radiate in a very focused pattern. It's kind of unintuitive. And by the way, the same thing is true of antennas. If I can get to that a little bit later. So what I want to do now is just kind of go through kind of some tones, and just to let you know that human hearing is generally between 20 hertz, which is 20 cycles per second, and 20,000 hertz. So we did a little experiment earlier today, and I think myself and Nicole, I think we tapped out at about 10,000 hertz, and beyond that, we couldn't hear it. It was too high for us. You unfortunately you begin to lose your high frequency hearing with age. On the other hand, I'm trying to remember your name. Juwan could hear 30,000, something crazy. Yes. I don't know how, but yes. Um, okay, so why don't we start? What I have here is just a signal generator, and it's going to play a pure frequency, just a pure sine wave, and you're going to notice that they don't really sound that great. But what I'm going to do is I'm going to move kind of the speaker out here, and then I'm going to just crank up the frequency so you can kind of hear what's going on here. So okay, so let's see. So I think we already determined that this microphone was having problems. Yeah. So all right. So this is 150 hertz, and I'm wondering if they can tell me if they can hear this. Okay. So if you come and listen to the speaker, it's not coming out of there. It's all coming out of the woofer, and I can go lower. I'm wondering if they can hear that. Can you guys hear that?
Yeah.
Okay. Well, let's keep going. Can you hear that?
No.
Okay. So the microphone is an issue, but I don't think the microphone is an issue with the high frequencies. So this is going to be painful, okay? Okay, this is 1,000. This is 1,000.
Fun.
I
Okay,
think I
let
can hear it.
let's go 2,000.
I can barely hear it, but it's there.
I can still hear it.
Yeah, I can still hear it.
Let me know if you hear a drop off as I move the microphone, if you hear a decrease. So I'm holding it right in front and then I'm gonna move it off to the side. You hear it getting louder as I move it towards the middle of the speaker? Okay, that's going to be even more pronounced as I increase the frequency. And I apologize. I'm going to increase the frequency. What's the frequency, baby? All right, we're going to go to 8,000 kids. Going to 8,000. Really? Can anyone hear this?
Barely.
I can hear it.
Not anymore. I can't hear it. I can hear
Just
it there.
barely.
I think 6 is good. So I want to go as high as we can in frequency, and so what I want to demonstrate is the directionality. How you really have to be in front of them to hear these frequencies, and when you get off the side, it really drops off. So I'm going to shut up and put the microphone in front of the speaker. Can you guys hear it go in and out as I'm moving the microphone around?
Yeah.
Yes.
Yeah.
Okay. All right. So, um, well, I think it's already difficult through the microphone. I think this thing has issues. Okay. Uh, can anybody hear this?
I can.
Okay,
I
I'm going to keep
can't.
going. Okay. Anyone hear that?
Nope.
No.
Okay.
Can just barely hear it.
That's 12,000. And I think the microphone is band limited as well. Okay, so we didn't design these things to play pure sinusoids. We designed these things to play rock and roll. So unfortunately, all I have is my Mark Knopfler CD. So that's just going to have to do. But if you guys come here, you can put your own music on. So, all right, I need to rearrange things here.
Let's laugh, my friend. Don't you love the sound?
What's a decibel meter?
At the end, down in the gutter with the mad old soldiers, down in the scuppers with the drunken sailors, down in the gutter with the mad old soldiers.
Can, it's Mark Knopfler sailing to Philadelphia. Is that good or bad they want to know what it is? Okay, I'm getting some thumbs
My
up
teacher
and
Mark Maxwell said it's good.
okay, good. So so what makes a speaker good? I mean, let me turn this down. and I'll turn it back up. A great speaker will fool you. If it sounds like somebody's there, it's not how loud it gets. It's not any. It's how natural does it sound? And you know, these if you were here, I mean, we're going through a microphone and all that, but these things, they sound amazing. Yeah, I'm getting nods in the background. They absolutely sound amazing. Maybe my choice of music isn't amazing, but the speakers are amazing. So I'll turn up for a little bit more, and then I guess I'll start my PowerPoint thing, if that's okay. Yeah. Okay. So, oh, you know what? I forgot to bring, because everybody loves Dark Side of the Moon. Yeah.
Yeah.
Does anyone want to do karaoke? No.
They had you crying, they came up smiling. They had you crawling and you came up flying.
Little Van Morrison there.
They had you crying, you came up smiling. And the last laugh, baby, is yours. And don't you love the sound? The last laugh going down. Oh, don't you love the sound of the last laugh going down?
Okay. Thank you. You know, that last thing that I did, where I put the microphone really close to the speaker, was to illustrate one more thing. And that is, these speakers don't sound like you're close to them when you're close to them. So unlike your regular speakers, if you get close to a tweeter, it's really getting loud quickly as you move closer to it, because that sound is kind of radiating out of this point in this kind of spherical wave pattern. The sound is radiating out as what we call a plane wave. So it already sounds like it's coming from far away. So you can put your ears right up next to these things and it doesn't sound like you're really close to them. Now, you've all heard of planar headphones. That's what these are. They're planar, and it's just a much more natural sound. There isn't that detection. Gosh, I'm getting really close to the sound source. Okay, is there a break in this, Andrew? No, I mean, I just got to.
Dr. Monk, we have a question in the chat box about
okay,
how were these speakers made exactly? And could you just go in a little detail on how long and how many students were involved in the process?
Yeah, well, I had 3 students working on them. And I think this was back before we had our new engineering building and our great facilities. So these were literally completed in my garage on weekends. And I think the biggest expense was feeding 3 guys for like 10 weeks every Saturday, you know, and they ate a lot. One of them was a weightlifter. So so how are they made? Well, I guess the part that you're probably most interested in is how we made the electrostatic panels. And if you just allow me to put the microphone down, I'll just kind of, again, just kind of show you this Mylar. And you've probably heard of Mylar. It's something that's actually used in capacitors and things like that. But it's basically, like I said, it looks like saran wrap. And let me kind of lift it up here. So the first thing we would do is, on a really nice clean surface, is to pull this Mylar out and tape it to the table, and just keep pulling it tighter and tighter till it's really like a tight drum head. And then the next thing we would do is get this 3M double stick tape, and we're going to basically lay strips down here on the perforated metal. We're going to kind of lay it out exactly like you see it here. So there's tape along the edges here, and then, well, there's the double stick tape along the edges, and then there's 3 more strips in the middle. And so once we have that the way we like it, you know, we peel off the other side of the double stake and double tape, and we very gently set it down on the mylar that's taped to the table. We then take a razor blade and cut out the shape of the panel here. So now we have a panel with mylar on one side that's adhering with the double stick tape. Then what we have to do is we need to put that really large voltage on that mylar. The mylar itself is an insulator, so we need a way for the charge to flow on the panel. And so what we need to do is put a coating of something on the mylar that it allows charge to flow. But it's a little bit tricky because it can't be really conductive. It has to be something that's still pretty resistive, but not perfect. Not what we would call a perfect insulator. So you want charge to be able to flow on the mylar, but not too well. And let me see if I can find what else we need here. We need a way to make contact. Well, I did not know I was going to get this question, obviously. We also have some copper tape. If you've ever seen copper tape that people use when they do stained glass, we take the copper and we press it against the mylar that has the conducting, so we can make contact with the mylar. Then we make another panel with our double stick tape. And we, again, very, now it's even more critical, carefully align them. And then we squeeze these 2 panels together. And there will be one wire coming out of the bottom of the panel that is making contact with that piece of copper tape that's running along the bottom. That's how we're getting our voltage that's going to be applied. And the charge on that mylar is going to basically flow onto that mylar because we have that very slight conductive material on there. So that's how we make that panel. And after that, it's just a question of designing the filter, which if you want to kind of put the camera on the crossover. So then it's a question of designing this thing here and determining, you know, what frequencies, what tones do you want to go to the panel, and what tones do you want to go to the woofer. This other transformer here I've mentioned before is absolutely necessary, because without it, the voltages are too low for you to be able to hear it. So I have a couple extras of these, and again, these are again very unusual step-up transformers, because it's not normal that a step-up transformer steps up that much. And so basically what it requires is a lot of turns, a lot of windings wrapped around this iron here. And I guess the only other part of the speaker that we need to concern ourselves with is the circuit that's going to apply that 2000 volt DC voltage to the mylar. So, and then of course there's cabinet making. You know, there's you know, we built the cabinet for the woofer. We built these panels. So well, basically we built everything. So the only thing we didn't construct was the woofer. Um, spec- somebody asked that question? Oh, well, the woofer is your kind of your standard driver for, that's able to produce the low frequencies, or, you'll be able to hear it. If you could apply low tones to a tweeter, but you wouldn't hear it. It's not very good at converting that. Well, yeah, this is I think a 10-inch or whatever. So, yeah, does that answer your question? Kind of. I mean, if you come here, I'll show you exactly how to make them. I mean, we have we have lots of extra materials to do. We actually found a mother load of extra perforated panels. So I think the big expenses, because you did ask about cost, would be those transformers. And if you want to make a really good crossover network, some of these capacitors and inductors are a little more expensive than you'd pay for cheap ones, but you do need to get good ones. Are there any other questions?
Please feel free to unmute if you do have questions. You can ask them.
Okay, and I don't know if I answered everything, because I think one of them was how much it cost. I think we end up spending $600 each for everything.
What was the budget for this project?
Well, I think we end up spending $600. Yeah. I mean, it was, not very much for the quality of these speakers, actually. So, and now I have a lot of extra stuff, so I could probably do it for quite a bit less than that now. I can start my PowerPoint presentation. So I guess a little bit about myself. I was actually born in Denmark. My parents immigrated when I was several months old. My dad ended up going to Ohio State in around 1963 to get his PhD in electrical engineering, and that's kind of how we ended up in Columbus, Ohio, which is where I grew up. My first degree, and I don't have this on there, but my first degree is actually in finance, and I actually worked in a bank for about a year and a half as a financial analyst. And then one Saturday, I had to go visit my dad in the lab that he was working with some grad students, and they were doing some measurements of an antenna in an anechoic chamber. I'll show you a picture of what an anechoic chamber looks like here in a little bit. But I was just observing them running around, having fun, being excited, and getting paid for it. And it was just a real epiphany, like, because I was just thinking that nobody at the bank where I worked as a financial analyst was really excited about their jobs. I mean, they did it for the money or whatever, but nobody loved what they did. And I thought, well, why not go back to school, be serious this time, and see if you can find something you love doing. And of course, I didn't know whether I could do math and physics and all that. And I did have a plan B, which was to go into geology. My wife is a geology professor, so I always tell her that was my plan B. Anyway, I got a BS electrical engineering at Ohio State in 1990, MS in 92, and then I did a PhD in geophysics. So a lot of the work that I've done is involved electromagnetics. For my master's, I was looking at how electromagnetic energy is scattered from these ceramic wing structures, so basically space shuttle type stuff. And of course, one of the things they were interested in is how the electrical properties of these materials changed as they were heated, because one of the things we look at is something called the permittivity and permeability of materials. And they can change quite a bit as you heat materials. So NASA was very interested in that. And I did some work on that. So for my PhD, I did kind of an even more interesting problem, which was inverse scattering problems, where you send an electromagnetic wave at something, and then you try to image what that object was based on how it scatters its energy. So it's a bit more challenging of a problem because in not knowing what the object is, you're kind of dealing with what's called an ill-posed problem mathematically, which means, you know, you pretty much have to turn your brain inside out to find solutions if they exist. I did a lot at Ohio State. I also did a postdoc at the Bird Polar Research Center, which is a really, really top research center in polar studies. So upon completing my postdoc, I ended up at University of Alaska, Anchorage, and I actually taught physics my first year here. And I've been teaching double E ever since. So I generally teach, my main courses are electromagnetics, antenna theory, um, uh, circuit theory, signals and systems, and I have taught geophysics and physics, as I mentioned. So I think I just click on this to get it to go, right, Andrew? Or hit enter. There we go. So, oh, one of my pictures is gone. So I'm kind of have some real general EE subdisciplines. Not everything is showing up. So up here in the upper left-hand corner, I have electromagnetics, and this is actually the anechoic chamber that I was kind of discussing earlier, that my dad was working in, measuring some antenna properties. So if you've ever seen a room like this with these like cones on the wall, well, there's actually two types. There's acoustic and electromagnetic anechoic chambers, and basically the cones are there to either absorb acoustic energy, which would be sound, or electromagnetic energy. So the whole idea is to have a closed room where any sort of wave that hits the wall doesn't bounce back. So it looks like you're in space, right? If you were in space and you sent a wave out, it never comes back. Okay, now why wouldn't you go outside to do this? Well, actually, that's a good question. They used to do these measurements outside, and that was before, you know, the Russians had satellites that could kind of look at what we were doing. And with the advent of spy satellites, it became necessary to be able to make measurements of things in a closed room. And these rooms are generally enormous. They're like a couple basketball stadiums. So one of the things that we were interested in at Ohio State was designing aircraft that are hard to see from enemy radar if you're doing military aircraft. And so we would get models of aircraft and send waves at them and measure how those waves reflected off that aircraft and measure how low something called the radar cross section of that aircraft is. So we were trying to make these things invisible. Now, I didn't personally do this. This was my dad's area. And one of the things that he did was made antennas invisible, because that turns out to be the biggest reflector on your aircraft. So electromagnetics is a huge subdiscipline in electrical engineering. Power, if you're up here, is also huge. And as you guys may be aware, I mean, Texas recently had a major power grid failure, and I guess power is one of those things you don't really think about until something goes wrong. But of course, I mean, power is getting a lot more interesting because people are interested in alternative energy, and some of the challenges of connecting to the grid, and all these things are issues that one of our faculty members, Professor Hadari, deals with. Another big topic in electrical engineering is communications, which would be, you know, transmitting information from one place to another, whether it's cell phone, internet, or what have you. And so I have a picture of a communication satellite here. The picture that is missing in the lower right-hand corner, I think, was a controls. So controls is another EE subdiscipline, and one of our faculty members, Professor Kuplik, is a controls guru. He's a PhD from Colorado School of Mines. So let me see how many of these I can get through. Oh, there it is. Okay, there's controls. I don't know why I needed to hit that twice. Okay, so one of the projects that we've worked on in our electromagnetics lab, which by the way is the lab that I'm in right now, is a step frequency radar system. And radar systems are incredibly versatile. I mean, the things that you can do with them depending on what you're interested in. I mean, one of the things you can do is determine how fast an object is moving. So you probably all have heard of Doppler radar, and this is what police use to determine if you're speeding or not. So they basically send a signal at you, and a signal comes back to them, and the higher the pitch of that signal with respect to the signal they sent, the faster you're traveling, and they can tell if you're speeding. So we built a Doppler radar first. It's the most simple kind, and then we got into the ramp frequency, and finally we're into the step frequency. So we're making the radar more and more sophisticated. And one of the things we might be interested in is, you know, how far away is an object, or is there a target out there, and what does that target look like? So what you see right here is our can you guys see my cursor if I move this around? I think you can, because I'm screen sharing, right? Yeah, we have two antennas here. We have a transmit and a receive, and we're sweeping the frequency. So in other words, we all know what frequency is now. We're going from right? We're increasing the tone, and we're measuring what comes back. And from that information, we can tell where the object is, how far away it is, and we can generate these plots like the one you see over here on the right. And the lower screen right here is basically what we're seeing is coming back from us before we do all of the fancy processing we have to do to actually extract the information that we need out of the signal. There are a lot of satellites in orbit. I showed you a picture of a communication satellite. This is a picture of the Canadian radar Sat-1 satellite. And this is one of many satellites, although it was one of the first that's basically been put into orbit to obtain information about the surface of the planet. And there's all sorts of sensors on this satellite, but the one that we're interested in is this radar sensor. And so what we're able to do using really, really fancy signal processing techniques is to generate images of, in this case, Greenland. Whoops, I need to go back. Generate images of different continents, in this case, Greenland. You kind of see it looks kind of like a quilt work, and each of these swaths is something that the radar generated as it was passing over Greenland. So all of these satellites are what's called polar orbiting. They orbit from the North Pole to the South Pole, and as the Earth rotates around, they're able to image the entire Earth after like 6 to 12 days, and then it just repeats itself. So one of the really, really tricky things that we've done is to be able to generate images that have resolutions of several square meters. I mean, so that each pixel is like a couple meters by a couple meters, which is really remarkable and requires some really fancy processing called synthetic aperture radar, which is what SAR stands for. But one of the things that I did using this data and some other data was actually to determine why exactly in this image, if you look at this image to the very right here, you see what looks like mountains and things like that underneath the ice. So one of the things that was really puzzling about these radar images is why you could see what looks to be the subsurface. In other words, what we would call the what geologists would call the basal topography, the rock underneath the ice. Well, the ice is 4 kilometers thick. That's 4,000 meters. The radar only penetrates several meters into this snow. It looks flat as a pancake when you're on it, and it turns out, well, it's not exactly flat. And there's a reason you can see what looks like the subsurface several kilometers down, and it's because, well, you kind of can see below that. So that was a really interesting project that I worked on when I was a postdoc. Oh, okay. Oh, this project here. Well, I mean, pretty far. So really what limits our ability to see how far something is with this is how we're stepping the frequencies. So we send a pure tone, and then we step to another pure tone and another pure tone. And if we want to see really far, then those steps have to be really small. So the one thing we have to ask ourselves is, how far do we want this radar to see? And that's going to determine what the frequency steps are that we're using. I can tell you kind of a good story about some data that they took in Greenland. They literally went onto the ice sheet and took some, pointed a radar that was kind of mounted on a tripod into the snow and measured what came back. And because of the frequency steps that they used, they could only see down 7 meters. That was the maximum distance they could see. And I'm looking at the data, and the guy that I was working with said, "Well, we're really interested in seeing 20 some meters. What can you do with the data?" And I said, "Nothing." He said, "Well, what can we do?" And I said, "Go back to Greenland and take the data, but make the steps, 3 times smaller." So that's a really good question. Another radar system is a pulsed radar, where you actually send out an electromagnetic pulse, and then you don't have to deal with your frequency steps or anything like that. Although, I mean, when an electromagnetic wave travels, it basically gets smaller as 1 over the distance squared. So it gets diminished in the energy that it carries rapidly, and then it's going to hit something and it's going to get diminished even further. So generally what you're measuring in radar, what comes back are really, really weak signals. I hope that answered your question.
Um, can this reach anything where it bounce back?
Well, I mean, so actually, I should say that the satellite that I showed is measuring reflections from the Earth's surface. So it's literally sending out a signal, and it's orbiting 200 kilometers above the Earth's surface. So just to give you an idea of what 200 kilometers is, airplanes generally fly at 36,000 feet, commercial airliners. And if you convert that to kilometers, that's about 10 or 11 kilometers. So these are orbiting, 20 times higher than an aircraft. And there's a reason why they have to be that high. They have to be absolutely out of any atmosphere. Or the atmosphere has to be so thin that there's no drag on the satellite. but yeah, I mean, they're basically getting reflections from the surface of the Earth, and that distance is at least 200 kilometers. Because the other thing that I didn't mention is that these radars actually have to look off to the side. They never look directly below them. They look at a swath off to the side. So I hope that answered your question, or I mean, so you can make the radar see as far as you'd like. I mean, if I want to go extreme, um, that Arecibo radar system that just kind of fell apart in Puerto Rico, I think, they were using that to image the surface of other planets, using really, really, really clever signal processing techniques that involve Doppler radar and all sorts of other cool stuff. So, almost as far as you'd like, but you just have to design for it. Yeah, here's some other things that we do here. I mean, we do electrical methods in geophysics. So we've measured ice thickness using radar, and if you see right here, this is he's a postdoc from Italy at UAF, and myself going across the ice of the Yukon River, kind of measuring the ice thickness for a village that wanted to know if it was safe to put an ice road on it. And so, we're basically measuring the time it takes for the wave to reflect from the bottom of the ice to the water. And, we were getting 5 feet thick, which is, by the way, safe to drive a tank on. Consistently, the only places the ice isn't 5 feet thick is where it's basically too shallow to be 5 feet thick. So another example, kind of off to the side here, is a road that was really problematic in Fairbanks with massive ice and things like that. So every year they were having to dig this road up and repave it. And so we finally went out there and did some geophysics and found that there are, using an electrical resistivity method, we create these images of what's going on in the subsurface. And what we're really mapping is how the electrical resistivity changes. And it turns out when something is frozen, it becomes very, very electrically resistive. And if it's pure ice, it's almost like a perfect resistor, like current cannot penetrate it or flow through it at all. And so we generate these images and we could tell them, hey, you have massive ice underneath the road here, here, here. And we kind of did this cartoon sketch up here where we were able to kind of tell them, here's where you have your biggest problems, but maybe you need to think about not living in Fairbanks, right? Some other work we do deals with the ionosphere. So I told you these satellites orbit, at least these polar orbiting ones, orbit around 200 kilometers above the Earth's surface. But there is, even though the atmosphere is really, really thin, there is an ionosphere. You're not in a perfect pure vacuum. You're not in pure space. And so it turns out that even though there isn't much up there in terms of atmosphere, there are gas molecules up there. And because of the UV radiation from the sun, what happens is when that sun hits these gas molecules, it ionizes them. And so what does that mean? Well, it means that there's so much energy associated with this ultraviolet light coming from the sun that it knocks an electron out of the orbit of a gas molecule. And so what happens is you have an ion just kind of floating around on its own. And now what's left is did I say an ion? I meant electron. You have an electron floating out on its own. And what's left is an ion that has a net positive charge. So you go from having something that you think would be kind of this vacuum to really having what we call a conductive material. And conductive materials, you know, if you subject them to electric fields, these charges move and you can bounce signals off of them. And it turns out that the ionosphere is kind of the way that you communicate using shortwave radio. You're literally bouncing a wave off the ionosphere to a distant location. And it's kind of interesting because otherwise, you know, the Earth, by the way, is a sphere. I know that there are rumors that it's flat, but they're not true. It's not true. The Earth is not flat. So, you know, there are kind of ways to kind of get around the curvature a little bit. But if you want to go great distances, if you want to communicate with someone in South America, well, you know, in the old days, you'd have to bounce the signal off the ionosphere. And a lot of people who got into studying the ionosphere are old people who are interested in ham radio, shortwave radio, and all that. So what I have here is kind of a setup that we have in Homer, Alaska, which is famous for really good oysters. We always get oysters when we go there. Yeah. And we basically use this facility to image the sky above two different locations. One of them is in Gakona, which is where the HARP facility is. And this is a really, really cool facility that allows you to basically modify the ionosphere above the sky where it's located. And what you see here is like a bunch of, these are called cross dipole. Whoops, I need to stop doing that. Back. These are cross dipole antennas, and there's a whole bunch of these things. And if you sync them with each other, it sends a really, really high energy electromagnetic, highly directional, just like our speakers over there, signal into the sky so high that it can modify the ionosphere, and we can measure what's going on in Homer, Alaska. Let me go back. Okay, am I out of time? Oh my gosh. You guys. Okay. Well, I didn't get through nearly everything. I didn't pace that very well at all. Any questions?
Dr. Monk, could you real quick just say, you know, what do you love about electrical engineering?
Well, I mean, I love the stuff that I'm showing. You know, I love electromagnetics. I mean, this is in our blood. My dad was an electromagnetics guy. My little brother has a PhD in electromagnetics. So one of the things I love about this area is I could write the governing equations that we study on something the size of a stamp. I'm like, these are our equations. And what's amazing is something so simple can explain so much and be so complex, and that we can do so much with it. I mean, we can predict how things are going to radiate. I mean, we can, you know, there really isn't any electromagnetic phenomena that we can't explain using these four simple equations. So I love that. I love actually teaching. I love being in the classroom and working with students. Unfortunately, I didn't get to some of the stuff our other faculty does. We have students who are, or faculty who are, Professor Kuplik, who's really great in controls, who does this really cool class where people build these inverted pendulum robots, which are incredibly complex and tricky. Professor Hidari is a power god. He has done phenomenal work with students who he's published with, and they present at national conferences. Professor Peterson is also electromagnetics guy and a electronics guru, former hammer thrower in college. Yeah, I was going to do a really cool demo, but we don't have time. So I was going to do a controls thing. I stole them up for it too. All right, how are we doing?
Good.
Does anybody in the audience have any questions?
Are you guys planning on making any more projects similar to this?
To the speakers,
Yeah.
if there's interest, yeah. I mean, anybody who come to my office and says, "Hey, Jens, let's build some speakers," I'll be like, "Yeah, let's do it." And we don't have to go to my house to do it either, because we have this stuff here. And I won't have to feed you.
And there is a question, do different models have different designs?
Oh yeah, yeah. I mean, there is no one way to do this. There are some really cool ways to convert electrical energy to sound. There are ribbon speakers. There are speakers that are plasma driven. I mean, they're just you can really use your imagination, and there are ways that nobody's thought of yet. So yeah, I think one of the exciting things about transducers is how creative you can be when you're designing them. Come up with something that works. Let's test it. Let's build it. You know. No, I'm just oh, somebody's dad said go Buckeyes. I'm just finally looking at the comments. So 117013 hertz. Okay. Keep going. Yeah, I guess that was the frequency. Somebody wanted me to crank the frequency even more. All right. Adios.
All right, so this is just to be respectful of everybody's time. We're going to end it here. If you do have questions, please feel free to reach out to us anytime. We're happy to answer questions. For me, if you're going to be an incoming student, please don't hesitate. Send me an email, give me a call. If you have program specific classes, our faculty are also more than happy to answer your questions. You're also going to be receiving an email survey. Please fill that out. If you fill that out, you are entered into a chance to win some College of Engineering swag. So get that in as soon as you receive that. And then also don't forget about tomorrow's presentation with mechanical engineering.
Thank you. Bye-bye.
You're welcome. Have a great night, everyone. I'll see most of you tomorrow.
Good morning. Have a good day.
Bye.